So thank you. I will talk about the interior structure of Uranus and Neptune inferred from the PLT data for H₂O and laser-driven shock loading. So planetary magnetic field is produced by convection of the electronic conductor in the planetary interiors. So planetary magnetic field has an important implication for interior structure. So as you know, many solar planets have a magnetic field. In the case of the Earth, Jupiter, and Saturn, do you have the pointer? Okay. So the magnetic axis are not so inclined from the rotation axis, while the magnetic axis of Uranus and Neptune are significantly inclined from the rotation axis. Moreover, this axis offset from the center of planets. So the morphology of the magnetic field of Uranus and Neptune are very different from the other planet. So this picture shows the component producing the magnetic field in the Earth. Iron and nickel produce the magnetic field, and in Jupiter and Saturn, the metallic liquid hydrogen correspond to the material, while in Uranus and Neptune, water, methane, and ammonia correspond to the material. Especially water is the most fundamental component in these planets, so the water may affect to generate such enigmatic magnetic field. However, the reason why such a strange magnetic field is produced has not been solved yet. In conventional model, the interior structure of Uranus and Neptune is such like this 3 layers model. But the dynamo simulation cannot reproduce such a non-dipole magnetic field by using this geometry. But recently, the dynamo simulation group suggested the new geometry, this one. This means the IC layer divides into the convective and the non-convective layers. So they obtained the non-dipole magnetic field, which is qualitatively similar to the those of Uranus and Neptune by using this geometry. So they suggested that this geometry is realistic. And subsequently, quantum molecular dynamics calculation predicted that the superionic water may exist in the interior above the 100 GPa from this phase diagram. As you know, the superionic water means that oxygen remains the lattice structure and hydrogen rapidly diffuse. So this water is believed to behave such a solid. So they predicted that this water may correspond to the main component of the non-convective zone, and this geometry is realistic from the material science viewpoint. In order to verify such a prediction of the theoretical studies, recently the P-low measurement under shock loading has been performed, and these data are in very good agreement with the QMD. QMD means the quantum molecular dynamics based EOS. This indicates that the QMD EOS is most suitable for modeling H₂O in the icy giant. While there was no consensus on the melting behavior of H₂O among a number of measurements such like this, but I determined the melting temperature of H₂O up to 72 GPa. These data indicate that the melting temperature is not so high compared with those of the quantum molecular dynamics QMD. And also this slope is gentler than that of the QMD. This fact indicates that the ice should not exist in the deep interior of the icy giant. So as I showed the previous slide, melting curve determined in the experiment is not in agreement with that of the QMD prediction. This fact indicates that the QMD EOS model is disputable for modeling the planetary interior. Indeed, the comparison between data obtained from the shock experiment and the QMD EOS did not even cover the temperature, only the P low data. So P low T, EOS measurements covering P low T, especially T at extremely high PT, is essential. But in fact, it's quite difficult to determine the temperature precisely enough to assess the EOS model. So I tried to obtain the data on not only the principal Hugoniot, but also the off-Hugoniot curves by using the precompression. By combining the precompression with the laser-driven shock compression technique can generate such a low temperature condition compared with the pre-compression, principal Hugoniot state, such like this. Sorry. Yeah. So here is the diagnostic system. We determine the shock density and pressure from the shock velocity of quartz as the shock standard material and the shock velocity of water sample measured by using Visor. Visor is one kind of the velocity interferometer. And I also determine the shock temperature by thermal radiation at 455 nanometer and reflectivity at 532 nanometer, measured by using the SOP, which is one kind of the pyrometer, and Visor, respectively. So shock velocity of quartz and water were measured by Visor. Quartz was used for the standard material in order to determine the shock density and the pressure of sample. So this figure shows the time record of shock velocity. As you can see, this continuous change in the fringe position indicates that the shock transit from quartz to water at this time. And also the shock velocity discontinuously change at this time by using the velocity, both velocity. We can determine the Hugoniot parameter via Rankine-Hugoniot relation and impedance mismatching analysis. And I will show how to determine the temperature. SOP measure the thermal radiation intensity at 455 nanometer, and the reflectivity was measured by Visor at 532 nanometer. By assuming that the emissivity vary only slightly as a function of wavelengths in this spectral range, we can determine the temperature via this Planck's law and the Kirchhoff's law. So this figure shows the time record of the thermal radiation intensity when the shock transit into the water. The intensity rapidly decreases, such like this, and by using this intensity and the reflectivity, we determine the temperature. Here is the results from the shock experiments. This figure shows the Hugoniot plot in P-low plane and the PT plane. This black plot and the red plot represent the data on the principal Hugoniot and off-Hugoniot curves, respectively. And this solid and dashed curve represent the Hugoniot curve from the QMD prediction, QMD EOS, and Sesame model. As you can see easily, our data are in perfect agreement with the QMD EOS. And then this figure shows the reflectivity data. Our data are also in good agreement with QMD EOS, QMD prediction. So according to our results, our experimental data for EOS is in good agreement with those of QMD, while the melting temperature of the QMD is high compared with our recent measurements. Here, the QMD determine the boundary location between solid and liquid by observing the mean square displacement of oxygen. However, the melt can be thermodynamically defined in an approximate manner. This figure shows the comparison of the Gibbs free energy between solid and liquid of aluminum, not the H₂O. We can determine the melting temperature where the equilibrium point. Therefore, such a free energy comparison between solid and liquid should be introduced in the QMD model in order to accurately determine the boundary location. So, according to our results, the non-convective layer does not compose of H₂O, so we have to find the other possible candidates. This figure shows the phase boundary of methane. Methane decomposes into the diamond and the hydrogen at the planetary interior condition, and also this phase diagram of the ammonia. Ammonia also decomposes into N2 and H2 at the planetary interior condition. Therefore, such a heavy species such as diamond or N2 should sink into the deeper side in the IC layer, and such a component can form the non-convective zone. Okay, in summary, our melting temperature are significantly lower than those of the QMD model, and our data covering P low T agree under the laser-driven shock loading agree with those of the QMD EOS. According to our results, non-convective layer in Uranus and Neptune should compose of not H₂O but C and N2. That's all. Thank you.
Dave?
A comment about what you have at the bottom of the slide. There is, of course, no requirement that you specify a phase for a layer. So all that you need to prevent convection is a compositional gradient. And that's a perfectly reasonable thing to have inside the planet. You don't have to invoke carbon, nitrogen, or anything. You just say there's a compositional gradient. And that's a perfectly reasonable thing for a planet to have because of what happens during accretion. A compositional layer can arise just from having some rock dissolved in the water.
Sorry, I can't understand what you... Could you please explain more the... Sorry.
Any other comments? Guillaume? You here?
You mean the pressure range?
Pressure range, yeah. Pressure range. The pressure range for the melting is quite lower than the one for the shock.
I see. So the highest pressure of the melting temperature is 72 GPa. And in this study, the pressure range is about 1 megabar. So not so different.
works qualitatively to explain the magnetic field of Uranus and Neptune, and it has a stable layer in it, doesn't really mean that there's a stable layer in the planet. Maybe there's other models to match
Okay. So I think we need to thank the speaker again.
Thank you again.